This lecture is about type safety. So we will consider type safety of simply typed lambda calculus. So for simply typed lambda calculus, we have defined two systems. The first is operational semantics, and the other is type system. So this operational semantics is sometimes called dynamic semantics because it deals with dynamic properties of a given expression. So by using this operational semantics, we can find out the meaning of this expression E. So if we have this judgment, then we say that this value V is the value of the meaning of this expression E. So we can find out the value V from this expression E at runtime. In general, we cannot find out this value V before running this expression. So we can find out the property of this expression E, namely its value is V, only at runtime. In that sense, this value V is a dynamic property of this expression. So in this sense, operator semantics is sometimes called dynamic semantics. Type system is sometimes called static semantics. The reason is that this type system allowed us to find out the type of a given expression even before evaluating it. So at compile time, we can find out its a property, that is, it has this type A at compile time. In this sense, this type system is sometimes called static semantics because it allows us to find out a static property of this expression. Now, we have these two systems, operator semantics and type system. But we have developed these two systems independently of each other. That is, when we were developing operator semantics, we didn't have this type system. And when we were formulating this type system, we did not recall the operator semantics. For instance, we did not assume call by value, or we did not assume call by name. We just assumed that there is an operator semantics. And independently of this operator semantics, we developed this type system. So these two systems were developed independently. Then there might be some possibility that these two systems do not respect each other. So for example, let's consider this expression: if true, then E1, else E2. If the expression E1 and E2 both have a type A, then the whole expression has type A. So this is stated in this type system. And according to the operator semantics, we reduce the whole expression to this expression E1 because this conditional expression is Boolean true. So everything looks fine, and that is because the operator semantics we developed and the type system we developed, they respect each other. They live in harmony with each other. But suppose that as a human being, suppose that we have made a mistake when we were developing these two systems. For instance, we might have made some terrible mistake in the reduction rule for this expression. So ideally, this expression is supposed to reduce the expression E1, but let's say we made a terrible mistake and the whole expression reduced it to some completely unrelated expression, let's just say lambda x a dot e, something like this. So then what happens is, let's just say this is lambda x dot x. Then what happens is, this expression before reduction has a type A, but after reduction, suddenly it has type A arrow A. And this is perhaps not what we want. And this phenomenon occurs because there is a bug in this reduction rule. The reduction rule for this if then else expression is supposed to produce expression E1 because this is Boolean true. But a mistake in formulating the reduction rule produces the wrong result. Instead of expression E1, we mistakenly produce this lambda expression. Then there should be something wrong with this operator semantics or the typing rule. In summary, we have developed these two systems, dynamic semantics or operator semantics and static semantics and type system. We have developed these two systems independently of each other. So we have to verify that these two systems are okay in some sense. That is, they don't have some design bugs. Then how do we verify that these two systems are okay? They live in harmony with each other. And the way that we verify that the two systems are okay is we have operator semantics with this reduction judgment, and we have this type system with this typing judgment. We prove two properties in type safety. First is progress, and the second is type preservation. This progress property says that if you have an expression that is well typed, then either expression E is already a value, or you can find another expression that expression E reduces it to. That's the progress property. The type preservation property says if you have an expression, a well-typed expression, and also reduction judgment, then this type preservation property guarantees that this new expression also has the same type A. So these properties constitute this type safety. So at this moment, we don't know if the simply typed lambda calculus with this operator semantics and this type system indeed satisfies this type safety property. But if these two systems live in harmony with each other, that is, if there is no bug in these two systems, perhaps we will be able to complete the proof of these two properties. If there is some funny bug in these two systems, for instance, this expression reduces to this lambda expression, then probably we will not be able to complete the proofs. So type safety is some way to verify that the two systems developed independently of each other, this operator semantics and this type system, are okay in some sense. They are safe to use. So we will try to prove this type safety, progress property, and type preservation property. If we manage to prove these two properties, we can say that well-typed expressions cannot go wrong. Which means that if you have a well-typed expression, it cannot go wrong or it cannot get stuck during the reduction. So for instance, suppose that you have this well-typed closed expression, something like this. It is well-typed and it doesn't have it doesn't have these pre-variables. Now we have this well-typed expression. Then thanks to this progress property, either it is already value, in which case we are finished. because the reduction is, there's no need to further reduce this expression, so we are finished. Or there's another expression, e prime, such that it reduces to e prime. So one of these two should be the case. So if it is a value, then we are finished. Now let's assume that it reduced to another expression, e prime. Now we satisfied the two conditions in the type preservation property. You have a well-typed expression here, and we also have this reduction judgment. Then, thanks to this type preservation property, we can say that uh, E prime also has a type A. Now we go back to precisely the same situation that we were at before reducing this expression. That is, we started with a well-typed expression, we end up with another well-typed expression of the same type. This expression E has a type A, and the resultant expression E prime also has a type A. So we are precisely at the same situation. So that means that the reduction can proceed for many more steps, but nothing wrong will happen along the way. You will never find some funny expression like 1 plus true or something like this. Starting from an well-typed expression, you will not be able to generate some funny expression like this. So that's what this phrase, well-typed expressions cannot go wrong, really means. And that's an easy way to summarize these two properties constituting type safety progress and type preservation. So one thing that we'd like to keep in mind is, in the case of progress, the typing context is empty. Whereas in the case of type preservation, the typing context is not empty. So here it is not empty. We may use any typing context. But in the case of progress, you have to use this empty typing context. So the question is why? And actually, it's pretty easy to see why. Let's first talk about this progress. So let's remove these. So in the case of progress, we are interested in whether this expression E reduces to another expression E prime. So we don't know whether it will reduce or not. So therefore, we require that this expression E be a closed expression. Otherwise, that is, let's say this statement that if, let's say this statement is if the gamma turnstile expression EA, then this progress statement is downright wrong. So for instance, if you allow any typing context here, we can easily find a counterexample, which is, for example, variable x. Under typing context, x colon a. So this is a valid typing judgment. Then this variable x is neither value, it's not a value, nor x does not, nor we can find a reduction judgment here. So it's not a value, and it doesn't have this reduction either. So you cannot find some expression like this. So this variable x is just a counterexample. So therefore, in the case of progress, we have to provide a closed well-typed expression, closed because this typing context is empty. So it must have basically no free variable. Otherwise, you may not be able to reduce the expression, for instance, this variable x. So in the case of a type preservation, things are slightly different because we already have some evidence that this expression E reduces to E prime. we already know that this expression it reduces. So therefore, there is no reason not to permit a typing context here, a general typing context gamma here, because we already know that this expression E reduces to another expression E prime. So that's the reason that in the case of type preservation, we allow this typing context gamma here, whereas in the case of progress, the typing context must be empty, so that expression E is a closed expression. To summarize, we developed the two systems, okay, type, uh, we, for simply typed lambda calculus, we developed phrase semantics, which is the dynamic semantics, and uh, type system, which is static semantics. And these two systems were developed independently of each other. So there is a slight chance that these two systems do not respect each other. For example, if we have made a terrible mistake in one of these typing rules or one of these reduction rules. So we have to now go back to these two systems and try to verify that these systems are okay in some sense. And the best way to do that is to prove type safety, where typed expressions cannot go wrong, which consists of two properties, progress theorem and type preservation theorem. So progress theorem says if we have closed expression, then either E is value or it reduces it to E prime. And type preservation says if we have the typing judgment and expression E reduces to E prime, then we have this typing judgment. So it literally preserves types. This expression E started with type A, and the reduction ends up with another expression E prime of the same type. So literally type is preserved.